Welcome back to another edition of The Explainer. Today we are going on a really fascinating journey. We're going to start by looking at the massive, macroscopic world, think ocean waves crashing against rocks, and scale all the way down to the microscopic mathematical rules that govern a single laser beam. So let's jump right in and demystify the physics of diffraction. But before we get into the lasers and the math, I want to throw a question your way. It's something you literally experience every single day. Think about this. Why is it that if someone is talking down the hallway, you can hear their voice perfectly fine even if you're sitting around the corner inside a room, but you can't see them? Both sound and light are waves, right? So why does one naturally bend right around the doorframe while the other acts like it hit a solid brick wall? This is the core mystery of wave mechanics, and the answer is exactly what we're unpacking today. Here is our roadmap for the explainer. We'll start with what diffraction actually is, compare it to interference, and then check out the Fresnel and Fraunhofer setups. After that, we'll break down the single slit pattern, and finally scale things all the way up to double slits and gratings. All right, Section 1. What is diffraction? Take a look at how these ocean waves are passing through that gap in the rocks. Notice how the parallel lines of the waves don't just travel straight through the opening like some rigid rectangular block. Instead, the moment they pass through that gap, they bend. They spread out in the sweeping, semicircular pattern, naturally wrapping around the edges of the rocky obstacles. You don't even need a physics degree to see this happening. Nature is literally doing the math for us right there on the surface of the water. So formally speaking, this exact phenomenon is what we call diffraction, the bending or spreading out of waves as they pass by obstacles or through a finite width aperture, essentially creeping into the region of the obstacle's shadow. Now let's circle back and answer our hook question. The amount of diffraction you get totally depends on the wavelength of the wave compared to the size of the obstacle. Sound waves? They have very long wavelengths, comparable to the size of everyday objects like doors, so they effortlessly bend and spread around them. Visible light, on the other hand, has a microscopic wavelength. When light hits a doorway, that doorway is impossibly huge compared to the light's wavelength, so the light just shoots straight past or gets completely blocked, creating a sharp shadow. And that is exactly why you can hear around corners but can't see around them. Moving right along to Section 2. Interference versus diffraction. To really grasp diffraction, we first need to set the baseline for its close cousin, interference. For light to create a perfectly observable interference pattern, it has to play by some very strict rules. First, you absolutely need coherent sources, meaning the light waves share the same frequency and maintain a constant phase difference. The waves also must have the same polarization. On top of that, they need roughly equal amplitudes, and the path difference between them can't be too huge.
Now here's where it gets really interesting when you contrast the two. In interference, which relies on two completely separate coherent sources interacting, the low points, or the minima, are perfectly dark, and every single high point has the exact same peak intensity. But diffraction is a different beast. Diffraction is an interaction happening from just a single wavefront that originates from a finite width slip. Because of that, diffraction features varying intensity. The bright spots get dimmer and dimmer the further out you go, and those dark spots, they aren't always perfectly dark.
Okay, Section 3, the Fresnel and Fraunhofer classes.
These two classes basically describe the physical setups we use to actually observe diffraction. In the Fresnel class, the light source, the viewing screen, or sometimes both, are at a finite, measurable distance from the obstacle. Because things are relatively close, the incoming waves are spherical or cylindrical, and you don't use any lenses to observe the pattern. The Fraunhofer class, however, makes this brilliant mathematical assumption. It assumes both the source and the screen are infinitely far away. Now, practically speaking, we cheat this infinity in the lab by using convex lenses. The first lens flattens the incoming light waves into a perfect plane wavefront, and the second lens focuses that diffracted light right onto our screen. This visual brilliantly illustrates the difference. On one side, we have an effect similar to a Fresnel observation, an opaque edge casting a shadow. But if you look really closely at the edge of that shadow, it isn't sharp. It has these complex, rippling fringes. On the other side is a Fraunhofer setup. Here, the light passes through a well-defined slit, and thanks to those lenses, it projects beautifully clean, symmetrical, and distinct rectangular bands of light and dark onto the screen.
Which brings us to Section 4, the single slit pattern.
So, how do we actually calculate the pattern of light spreading out from one single narrow gap? Well, we use a three-step methodology. It sounds complex, but it's super logical. First, we imagine dividing the width of the slit into a massive number of tiny equal segments. Every single one of these segments acts as its own tiny source emitting secondary waves. Second, Because these waves travel to the screen at a specific angle, we find the path difference, basically how much further one wave has to travel compared to the wave right next to it. Finally, we just add up the resulting phase differences from all those little waves meeting at a single point to calculate the overall resultant amplitude.
Let's map those steps directly onto this ray diagram. Here is our plane wavefront hitting the single slit, which has a width we'll call E. The waves act like little secondary sources, spreading out everywhere. If we pick an arbitrary angle of diffraction, let's call it theta, we can track those specific parallel diffracted rays. Check out how the second convex lens catches all those parallel rays and elegantly focuses them so they all crash together at a single point P1 on our screen. It's right there at P1 that all those slightly offset waves interact and interfere with one another.
And when we actually crunch the math to calculate the intensity of light at every single point on that screen, we get a true aha moment. We can map the wavy theoretical intensity graph directly onto the glowing bands of the actual physical laser pattern. Notice that massive, brilliant central peak? That's our central principal maxima. Then, as we move away from the center, the intensity just drops off a cliff. The subsequent bright spots are incredibly dim by comparison, and sitting right between them are the spots where the light completely cancels itself out.
Those exact spots where the light totally cancels out, the minima, are governed by this one core equation. E times sine theta equals m times lambda. Here, E is the slit width, theta is the angle, m is an integer, and lambda is the light's wavelength. So the absolute most crucial takeaway here is hiding right in the math. If the slit width, E, is infinitesimally small, meaning it's actually smaller than the wavelength of the light itself, then this equation cannot be satisfied for any angle. The entire diffraction pattern simply vanishes. You absolutely must have a finite width for the slit to observe this phenomenon.
Finally, Section 5, Double Slits and Gratings.
Look at this incredible pattern. This is what happens when we use two identical parallel slits. When we add a second slit, we don't just get two separate boring patterns sitting next to each other. No, the patterns actually multiply. What you're seeing is a broad, sweeping, dashed line. That's the diffraction envelope from a single slit. But trapped inside that broader envelope are incredibly rapid, narrow, bright, and dark bands. Those rapid bands are the pure interference fringes created by the two slits interacting. It's like the single slit diffraction is acting as a volume knob, perfectly controlling the overall intensity of the interference fringes contained inside it.
But hey, we don't have to stop at 2 slits. We can scale this up to thousands of slits. When we do that, it's called a diffraction grating. It is simply an arrangement of a massive number of parallel slits, all exactly the same width, separated by equal opaque spaces. If the slit width is E and the opaque space is D, then combining those two, E plus D, gives us what's known as the grating element.
And when you send light through thousands of slits at once, something spectacular happens. Because you have so many sources interfering, those bright spots, the principal maxima, become incredibly sharp and needle narrow, while the dark regions between them become super wide. And because the exact angle of those sharp bright spots depends heavily on the wavelength, if you shine plain white light through a grating, it acts like a superprism. It splits the light completely apart, producing a brilliant, multicolored spectrum where every specific color peaks at its own precise angle.
So, after looking at all these categories, single slits, double slits, gratings, I really want to leave you with this profound conceptual takeaway from our source text. Diffraction is simply the n approaches infinity limit of interference. Basically, what this means is that despite all the different historical names and complex categories, interference and diffraction aren't completely different beasts. If you take the interference of n tiny slits and push n to infinity, you literally get a single, continuous, finite slit. At their fundamental limit, they are exactly the same phenomenon describing how waves combine.
Which leaves us with a truly fascinating thought. Just by observing how water ripples through rocks, physicists were able to build the mathematical foundation to understand exactly how light waves act, how they bend, and how they split into a spectrum. If simply watching waves bend in our everyday macroscopic world can reveal the invisible properties of light, what other macroscopic phenomena out there hold the keys to unlocking the universe's most deeply guarded quantum secrets? Definitely something to think about the next time you're listening to a voice echoing around a corner. Thanks so much for joining me on The Explainer.